All right. So just to kind of get things going here, we're doing an investigation of Euler's formula. We're comparing vertices, edges, and faces. There's trying to find the relationship of those three. So what we do is we're going to take some polyhedra, turn them into graphs, count things like this has 1, 2, 3, 4, 5 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges, 1, 2, 3, 4, 5 focal or faces. And then for all these others, it's pretty much the same thing. This one's a triangle within a triangle. Love this one. And so this is going to give us 2, this has 6 vertices, 9 edges, and 1, 2, 3, 4, 5, 6 of those. I missed something somewhere. 1, 2, 3, 4. Oh, I counted twice outside. Okay, good. So this one's 5. All right, and this one, same idea. You have a triangle, but you have a point here. So you have 1, 2, 3, 4 vertices, 3, 6 edges, and 1, 2, 3, 4. 1, 2, 3, 4 faces. And I think they did the same thing with this one. Did you figure it out? Okay. All right. Then, when we get to these are really interesting, I think. This one with 2 vertices, 1 edge, and how many faces? 1. This one has 6 vertices, 1, 2, 3, 4, 5, 6 edges. And how many faces does D have? Only 2. 1, 2. Yep. This one has 3, 6, 7. Is that right? And 1, 2, 3, 4, 5, 6 edges. How many faces? 1, 2, 3, 4, 5, 6. I think that's all right. And then for focal points or focal, I keep thinking of the physics. Faces. There's only 1 face on this whole thing because nothing's closed. All right, and you can do those other 2 as well. It's all the same stuff. So did anybody come up with which 2 would you put together? Yeah, if you take V plus F, what do you notice every time compared to E? Every single time when you pair these 2 together, the sum is what? It's E plus 2. Yep. And so for Euler's formula, the edges plus 2 will be equal to the vertices plus the faces. And of course, you can say E is V plus F minus 2. This is called Euler's formula. Now, I'm not going to do this, but I'm going to give you an opportunity. You can prove this using math induction. Nice little challenge. It's not in my book, so I don't think you can just find it anywhere. You could prove Euler's formula using math induction. N equal to 1, N equal to K, N equal to K plus 1. You remember that. So what you just unearthed was Euler's formula. This is, you can go either way with this. If it's planar, this is the relationship. If you have this relationship, that means the graph is planar. So that's a cool way to prove whether something is planar or not, is do those add up. Okay, so we're going to do some proofs. I'm going to use this example, then we're going to do a couple together, and then we'll turn you loose on a few proofs here. Prove by contradiction, and what that means is assume the opposite and prove it doesn't work. Okay? So if I want to prove that, well, I can't think of any really good examples, but by contradiction, you're going to prove the opposite. So we're going to prove that this is not planar, so we're going to suppose it is. We're going to suppose it is planar. Okay? So if we have a bipartite with 3 and 3, how many vertices is that? 6. And then if it's complete bipartite, how many edges will that be? 9, right? Yep. Okay, so since K33 has 6 vertices, 9 edges, by Euler's theorem, E plus 2 equal V plus F. How many faces should there be? Well, it should be 9 plus 2 should be equal to 6 plus F. And yeah, 11 minus 6, F is equal to 5. That's what we should have. So we're assuming that it is planar, then there'll be 5 faces. So if there's 5 faces, this should work out. Well, here's where the rub is if you put a bipartite 3 by 3, okay, none of the faces in the plane are going to have triangles. So let's kind of go back here. Let's say we had a 2 by 1, okay, right? How many, there's 2 faces, how many edges to that face? 3. Let's say I have a 2 by 2. Okay. And how many edges on that face? 4, right? Okay, so it says here when we represent these with triangles, each face is going to have at least 4 edges. What they mean by that is if we go by 2 by 3, then we have here, here, like that. And this one was planar, wasn't it? Or was it not? I can't remember. Yeah, that's right, because this is the one where we went straight up from here and then back to here, was it?
You did a W last time that was straight up.
Yeah, but I did them a little backwards. Oh, that's not right. I see what you mean with the W. Okay, so we have the W, and then we went here to here, right?
Yep.
And then this one we went to here, right?
Yep.
Okay, so there we've got them all, and now it looks like it's at. Now, how many vertices are there on each face this time? No, these are bipartite. They are not connected. So my question is, how many edges are there for each of these faces? 1, 2, 3, 4. 1, 2, 3, 4. So when we say at least 4 edges, for these triangles, there should be at least 4 edges on a face. So if there's 5 faces, how many edges would we predict? 20 edges. And we kind of show that by looking at those smaller examples and saying, okay, with those triangles, there'll be at least 4 edges on a face. That means we could expect 20 edges. Now with K3, what we're looking at there is, in doing this, we counted the edge of the boundary on the faces, has at least, when we counted all of those faces, the faces overlap. So the total number of edges should be that number, 20 divided by 2, because it's like degrees. It's going to add up. You divide by 2, and you'll get the edges. What's the problem with this edges 20 over 2? This is not equal to 9. So therefore, K33 is not planar. So one more time, what I did is I assumed that it was planar, figured out the vertices, faces, and edges, and then I kind of figured out how many edges on a face. And once I knew how many edges on a face, I estimated how many edges there should be. And then when I divide by 2, I'll get the total edges. This is edges on faces. This is total edges here. And those aren't equal, so therefore it's not planar, is how we proved it. I'm going to give you a chance to do that. Go to the next slide. Yep. So for this one, the first step, we're going to assume, don't abbreviate that, assume K5 is planar. Okay. And then how many vertices is this?
5.
Yeah, it's 5. How many edges will that be? Yeah, K5 means it's all of these connected and all of these connected. I'm going to go here. I'm going to go. Yeah, we can just do it this way. It's not planar yet, but maybe we can do it. I don't know. Maybe we can do it. So how many edges is that again? 10. Okay. Then how many faces should there be according to Euler's? Yes. So E plus 2 equals B plus F. E is 10 plus 2 equals 5 plus F. So this should be 7. Okay. Now the part that's tricky is how do we figure out how many there are per a face? What could we expect there to be per face? So what I did is I did this. There's the 3, and there's 3 per face, right? If I did 4, how many are there per face? 3. So there are 3 per face here. There's 3 per face here. What do you expect that to be?
4. 3.
Probably 3, right? So you would expect 3 edges per face.
Why would you if a graph's complete, all the edges have to be connected to one another, so any face in that is going to be a triangle. So anything that's not a triangle doesn't have all the edges connected.
Yeah, and you can say that as a triangle, or you can just kind of look at the pattern here. You expect 3 edges per face. So then you should get the total edges should be equal to 7 times 3. And then with all those faces, there's duplicates, you just divide by 2. What's the problem with this? It's a fraction. That's a fractional edge. By the way, what is half of an edge? There is no such thing, because where is that half? It doesn't make any sense. Since half edge doesn't exist, then K5 is not planar, which is what we wanted to prove. Yeah, it takes a while getting used to it, but just what are the obvious things? That's what you write. Patrick.
Can you also say that
Say that again.
So, like in the...
Prove that if a simple connected graph, if the vertices are greater than 3, or connect with v greater than 3 vertices, is planar, then E is less than or equal to 3v minus 6. So we're assuming that it is planar. So I would say if your graph G is simple and planar, tell me about the degrees of each face. Of each face that comes up. I'm going to write each face. What does it have to be greater than or equal to? 3, right? Because if you only had 3, how many degrees on that face? 3, right? What if they weren't connected like this? How many degrees on that face? 6 for that one. But you see where I'm coming from for at least 3 or more?
That's just 4.
What?
Oh, yeah.
This one's 4? 1, 2, 3. Yeah, I think you're right. It is 4. 1, 2, 3, 4. That would be 4, and this would be 3. So we would say greater than or equal to 3. Now, I don't know how many faces we have, but let's say we found the sum of all of the degrees of the faces. Mm-hmm. This is the sum of all the degrees of those faces. Well, we kind of talked about that earlier today. If you added all these up, they should be compared to what of the edges? Twice that for all 3 faces. So if you have 3 faces, the sum of all of the degrees of those faces will be 2e. So this is the leap. You're saying this is what's given. You're given that the degrees, each face is greater than or equal to 3. Now when you add all up these, sum of all these, it's like 2 times the edges, greater than or equal to 3 times the faces. Now it's kind of cool because what can you substitute f with? What's f equal to? Yep, so you have 2 plus e equal v plus f. So f is equal to 2 plus e minus v, right? So we'll put that in, 2 plus e minus v. So this will be 2e greater than or equal to 6 plus 3e minus 3v. And go back, what are we trying to look for again? E, solve for e. So I'm just going to get, I'm going to subtract 6. I'm going to add 3v. I'm going to subtract 2e. And so that's going to give me 3v minus 6 greater than or equal to 3e minus 2e is e. Is that what we were trying to prove? E is less than or equal to 3v, proven. Okay? And that's how you would use that to prove that relationship of connected graph v greater than 3 is planar.